Hello, everyone. How are you? I trust you guys. You're all doing great. James from JT Smith Tutoring here. It has been a while since I came your way. To be precise, I've been absent from this for almost 3 years. But I'm glad that we are back and we are still in the business of keeping you mathematically informed. So we are going to continue from where we left. So today we are looking at another example of how to determine the solutions of a linear system without actually working it out. Right, okay, cool. So we all know that when we are dealing with a linear system, there are only three possible scenarios in terms of solutions. Number one, it's either we have exactly one solution, which we also call it a unique solution. Number two, we have infinitely many solutions. Number three, we do not have any solution at all. All right. So we are given a question here. Consider the system given by the augmented matrix below. The system is consistent for, so this term consistent, it means that it has got a solution. And when we are dealing with that aspect of having a solution, there are two possible scenarios, exactly one solution or infinitely many solutions. So that is what we are going to be considering right here. But if the question had said the system is inconsistent, then that means the system does not have a solution. So we are looking at for what values of K will this system give us either exactly one solution or infinitely many solutions. So I didn't want to whatever with this whole thing. So I actually answered already before I looked at the video. All right, cool. I want you to look at the notes that I have here. Step number one, we need to reduce the given augmented matrix into either row echelon form or reduced row echelon form. Number two, we need to look at the last row to determine the solutions of that system. And this is how the last row of that row echelon form matrix or reduced row echelon form matrix is supposed to look like. If it is no solution that is inconsistent, it means this is the situation here. So for instance, if here say I have two, it's like you're having a scenario whereby you are saying 0 is equals to 2. We know that that statement is not true. It's a contradictory statement. Hence, we conclude no solution. If it has got exactly one solution, this is how it's supposed to look like. So there is supposed to be any real number except 0. And then for it to have infinitely many solutions, that entire last row, after you have converted it into either row echelon form or reduced row echelon form, it must be entirely zeros. Okay, beautiful. So look at this. I'm looking here. So K squared minus 1, I'm looking first here at exactly one solution. This must not be equal to 0. This part here must not be equal to 0. Okay, beautiful. So you can see after working everything out, you see K is not equal to plus or minus 1. So literally speaking, what I'm saying here is that for this system here to have exactly one solution or to have a unique solution, K can be any real number as long as that real number is not plus or minus 1. Okay, beautiful. We are going somewhere. Now, let's look at the scenario of infinitely many solutions. For this system to have infinitely many solutions, we need to make this a 0. We need to make this a 0. So we all know that K is going to be equal to plus minus 1. Okay, cool. This is after working this thing out. But hold on. If I plug in 1 here, I'm going to get a 0 here. If I plug in here 1, I'm going to get a 2. So I'm having that situation which I described earlier on. 0 is equals to 2. So that makes it to be inconsistent. So no solution in that case. Therefore, for it to have infinitely many solutions, this K must be equal to minus 1. Okay? Must be equal to minus 1 only. not the +1. Because once you put +1 there, it's gonna be no solution. All right, but now let's look at the given options. K is equals to 2 and K is equals to 1. Yes, K can be 2, but definitely K cannot be equal to 1. Because once it is 1, we know it is what? Infinitely many solutions. And also because of the AND operator which was used there, you can't have that situation whereby K is equals to 2 and K is equals to 1 at the same time. Okay, beautiful. So option A is out. Let's look at option B. Here, K can be equal to -2 or K can be equals to -1. So remember, if K is going to be equal to -2, boom, exactly one solution. If K is equals to -1, boom, we know infinitely what? Many solutions. Beautiful. Awesome. All right. What about option C? What is the difference between option B and option C? Remember the use of those logical operators. You can't have a K being equal to -2 and -1 at the same time. All right, wonderful. What about option D? Option D, when K is equals to 1, a +1, we know that there's going to be no solution. So I'm going to leave this for you guys to tell me what's going to happen if K is going to be equal to 0. And then if we've got none of the given options. So you can actually see from these options that the correct option is B. K is either it's -2 or K is -1. We are done. Perfect. Mama taught me something very important growing up. A good visitor knows when to leave, or she would say a good dancer knows when to leave the dance floor. Okay, cool, guys. So there you are. This is all you were supposed to do. So till we meet again. Whoa, 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 whoa. Did I say it right? Yes, Mama said a good dancer knows when to leave, or she would say a good dancer knows when to get off the dance floor. Okay, perfect. Yes, I got it right. All right, cool, guys. If you have any questions, feel free to ask any questions in the comment section. Till we meet again, don't do what I wouldn't do. All right, guys, I will see you soon.